Hi everyone, this is Worksheet 2.2, a microscopic quantum mechanical explanation for heat and work. Now, the main message that quantum mechanics tells us that we're interested to know is that a system is always composed of a series of energy levels. And what that means is that if we've got a system like we do that I've depicted here with this little box, is that if the energy is going in this direction, then the energy levels will be at various different places. And it turns out that in the case of an ideal gas, they sort of spread out like this as they go upwards. Now, this concept of quantum energy levels is identical to what you know about the hydrogen atom. So if you think back to general chemistry, then you learned that the hydrogen atom has a series of energy levels that the electron can be at, and this is completely analogous to that. Except instead of just talking about electrons, the atoms themselves occupy these energy levels. So if we say that this right here is energy level 1, let's go ahead and represent 5 atoms here by just drawing dots at that energy level. That means that there are 5 atoms at this particular energy level. And we'll denote the number of atoms at the energy level with N1, like this. Okay, so 5 atoms at energy level 1 in our gas. And then at energy level 2, let's say that there are only 3. So therefore, the number of atoms at energy level 2 equals 3. And then at this energy level, let's put 2. The number at that one is 2. And then at the 4th energy level, let's put just 1 for now. So at the number of atoms in energy level number 4 is just 1. Notice that there are going to be more atoms at the lower energy levels, and this is typically the pattern you'll see for systems, is that the lower energy levels are more occupied than the higher energy levels. Okay, so what does this tell us about the internal energy, U, of this system? The internal energy is going to be equal to the sum of the individual energies of all the different atoms. So the total internal energy is the sum of all the atomic energies. And the way that we can represent this is that it's the energy level, the energy of energy level 1 times the number of atoms that are in that energy level, plus the energy of level 2 times the number of atoms in that energy level, plus the energy of 3 times the number of atoms in 3, so on and so forth. And really we can just say that this is equal to a sum over every level I, the energy of that level times the number of atoms that are in that level. Okay, so we can represent a change in the internal energy by making a summation over the energy levels like we did over here for the internal energy. But what's going to change? Well, if the internal energy changes, there's only 2 possible ways that you can change it, and that is by either changing the location of the energy levels or by changing the number of atoms in each energy level. And so a change in internal energy is going to correspond to, if we want to keep the energy levels the same, then the number of atoms at each level has to change. Or we could change the location of the energy levels, but keep the number of atoms at each level the same. So what does this mean for a system that is changing in size? So if I've got a system that's going from a larger volume to a smaller volume, then the larger volume system is going to have a series of energy levels, just like I drew above. But quantum mechanics tells us, like if you do a particle in a box problem, that as you decrease the volume of the system, then those levels are actually going to spread out, and there's going to be more, obviously, up higher. So the height of the energy levels are changing when I change the volume of that system. And so if I keep the same number of atoms at each level, I've got 3 there, 2 there, and 1 there, then I've still got 5 down here at this lowest level, and then I've got 3 at this level, and then the same number at those higher levels. But see how the energy has increased because I decreased that volume and I've done work on that system. So therefore, this is a representation of work, changing the height of the energy levels themselves. Now, if I've got a system where its volume has not changed, but I have changed its temperature, then the energy levels are going to still be in exactly the same location. But if I've got a cold system, then the effect that that's going to have is that, say I've still got those 5 at the lowest level, and then I've got 3, and then I've got 2, and then up here somewhere I've got the 1. Oops, let me erase that. Then over here, when I increase the temperature, this corresponds to a change in heat. If I increase the temperature, then it's going to bump the atoms from those lower levels up into the higher levels. So instead of 5, maybe I have 4. And then up here, maybe I've got 4 there, and then up here I've got 2, and then there I've still got 1. See, so I've increased the temperature of the system a little bit, but because that atom jumped up to a higher level, then I've increased the energy of the system without actually changing its volume. So going back to the expression that I have on the previous page, the change in energy is a sum of keeping the energy levels the same, but changing the number of atoms at each energy level, plus changing the height of the energy levels themselves, times keeping the number of atoms at each energy level the same. What this corresponds to here is this is heat, Q, and what this corresponds to is work, W. And so that's the quantum mechanical form of the first law of thermodynamics.